Make sure my I was having battery issues this morning, so I'm sure we didn't get cut off in the middle of this. Okay, so I updated homeworks. So this is the complete list. So we have this homework on double integrals that's due this evening, and then we have this homework on polar coordinates. That is, uh, 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 um, shifting our functions to polar coordinates in order to more easily integrate them. So that will be due on the day of the test. And then there's this very short homework on triple integrals, which is not due till the day of the final. We'll have to see how well we do with polar coordinates today. It's well, once you've done some double integration and you feel a little bit comfortable with that, the switching to polar coordinates is not horrible. It's just a little bit of it's meant to actually simplify things in certain cases, but if you're a little bit rusty with polar coordinates, that may slow you down. Although we're not gonna, you don't have to have expansive knowledge of polar coordinates to be able to use the polar coordinates in the way we're going to be using them. So we'll have to see how well we do today and Wednesday as to how much of this we're going to include on the test on Monday, December 5th. So we may have to delay some of this to the final exam, which is on the 12th. So, but the test will certainly include through this homework, right, on double integrals. But I don't want to pressure us for Monday, that last test, more pressure than it's going to be already. Okay, so that's kind of where we are at the moment. Um, um, and for the rest of the semester. I'm going to resume the notes here where we were last time, and finish our another example with just a double integration, but with rectangular coordinates, and then we're going to start talk about switching double integration to polar coordinates, and why that can be useful. However, I have to correct a mistake. Last time we were doing this example, we were trying to compute this volume beneath this surface. So that's the surface z equal 4 minus x squared minus 2y squared graph there, down to the down to the xy plane, right? And so we were able to set that up with double integral. So somewhere here is the double integral right there that we can use to compute that volume. And then remember, that was a real challenge to actually evaluate that double integral once we got it set up. Okay, so that required actually a couple of a trig substitution, and then we actually got to a point where we were going to need another trig substitution. And at that point, we just said, well, let's just try using Wolfram alpha to finish the integral. But I also mentioned that so we finished that evaluating that double integral. But I also mentioned you can also set this computing this volume up as a triple integral, and I tried to explain how to set up that triple integral last time, and I got a little bit over optimistic in setting up the triple integral. Okay, so I left out some important details there. So I corrected that. Here's actually the correct triple integral to compute that volume. But and so so next time when we discuss a little bit more in depth triple integrals for computing volumes, I'll come back and revisit this example and try to explain this better. Why this is the correct triple integral to compute that volume. Notice what's nice about triple integrals for computing volumes is the integrand here is just one, right? So you have a very simple integrand, at least to start with. But of course, there's a trade-off there, right? Okay, you simplify the integrand. Here's the integrand when you have a double integral, right, to compute that volume. So with the triple integral, the integrand just becomes 1 to start with. But of course, the trade-off is you have an extra integral you have to simplify, right? Okay, so you're switching 2 integrations for 3 integrations. So there's a trade-off there. However, it turns out that because this volume is a relatively simple type of volume, although it may look complicated, it's a relatively simple type of volume because it's just the volume beneath the surface down to the XY plane, right? And most of the volumes that we've been computing have been exactly that type. Just you have a surface, and then you're just trying to find the volume beneath that surface, right, down to a region in the XY plane. And that's exactly what this situation is. So, and that's the case. It turns out there's a fairly rote way, fairly standard way that doesn't really require a lot of thought to set up triple integrals to compute that volume. Okay, so this is not it, however. All right, so I'll also show you how the more sort of easy way to set up the triple integral for this particular volume. So that triple integral is it works, but it's kind of unnecessarily complicated anyway. The setup for it. All right, so I just wanted to make that that little bit of a correction there. Okay. All right, so now we did have another example though with double integration. So so let's finish this example. So this is our last example with double integrals before we switch over to the polar integrals, right? So we were right in the middle of this problem last time when we ran out of time. Remember, we were trying to find the volume of this little, I don't know how to describe that, okay, kind of quarter of a globe, right? Okay, here, and that's the volume between this this surface, right? That paraboloid surface, which has this equation, z equal 1 minus x squared minus y squared. So that's the purple surface sort of in the background there, this paraboloid. And then, but intersecting with that paraboloid is this plane, okay? And so it cuts off a little piece of the paraboloid, right? This little cap here. And we were trying to compute, well, what's the volume of that little cap between the plane, which has equation z equal 1 minus y, and then that paraboloid, right? Okay. And so we mentioned how we were going to do that, right? We were going to find the volume beneath the paraboloid down to the xy plane. And then we were going to find the volume beneath the plane down to the xy plane. And then we would just take the difference of the two, right? Okay, so you would find this total volume beneath the paraboloid down to the xy plane, and then the volume beneath the surface down to the xy plane. And then if you take the difference of the two, that would just give you the volume of this little piece here, right, between the plane and the paraboloid. But so that was kind of the logic that we were going to use. So we actually had to set up 2 double integrals there, right? Okay, the volume beneath the paraboloid down to the xy plane, and then the volume beneath the surface down to the xy plane. But the problem with setting up the double integrals was trying to figure out what is the proper region of integration on the xy plane, right? We need to know what the region of integration is, or we can't set up the double integrals, right? We can't set up the limits, right, of integration on the double integrals. So what is that region, you know, in the xy plane that's beneath the paraboloid, you know, where the paraboloid and the plane intersect each other? And so we just gotten to that point, right, of trying to figure out in the xy plane what's the proper region of integration so I can set up my double integrals. And we had already decided, well, you know, the key to this, right, is to figure out what is this curve, right, where the plane and the paraboloid intersect each other. That would give us the what the correct region is, right, in the xy plane. So we were trying to figure out this curve of intersection, right? Where these two surfaces intersect each other. And, our knowledge of, intersecting curves, these are intersecting surfaces, but our knowledge of intersecting curves, right, suggested, well, we know how to do this, right? We'll just take the two equations for the two surfaces, right, and set them equal to one another. Okay. Notice when you do that, that gives you an equation in X and Y. So you have an equation in two variables, right? And you can plot that equation on the XY plane. All right. That the solutions to this equation, those will be the XY coordinates where these two surfaces intersect each other. In other words, those will be the XY coordinates that give us the same Z values. That is where these two, again, where these two surfaces intersect. So we just had to figure out, what is that? What is that equation, right? So what is that? What does the graph of that equation look like? What does the graph of that equation look like? Let's set that. Let's try setting that to 0, and see what we think about this, right? So let's move some terms from the right hand side to the left hand side, right? So these quadratic terms here will become positive. So when we do that, let's see, we get what? X squared plus Y squared minus Y, is it? Yeah, we have this minus Y, and the ones cancel each other. That's convenient. So we just get there. We just get 0. Okay. Have any idea what that thing is going to be? What that curve is if you graph that? Just from your experience with curves, any idea what that's going to look like? What? Maybe what? An ellipse, yeah. Okay. Actually, you're sort of right there, Robert. It is an ellipse, but it's the simplified type of ellipse. Actually, this is going to be a circle. Let me show you. Let's show you why. We can figure out why this is a circle by completing the square on the left-hand side here. You don't have to complete the square on the x squared, because x squared is x minus 0 squared, right? But on these two terms, you need to complete the square. So let me group the y terms together, and let me group the y terms together there and add a little space. So if you're going to complete the square on y squared minus y, how do you do that? Do you recall? You're going to add 1? You're being optimistic like I was last week when I made a mistake. All right. Okay. Yeah. It's a little bit harder than that. Okay. But your idea is correct. Okay. You do want to add something, Robert, but what do you add? You have to take this coefficient. Remember what you do there? You have to take this coefficient, which is -1. You have to divide that by 2 and square it. So you get 1/4. So what you're really adding in here is 1/4. Okay. So I'm going to add a 1/4 inside the parentheses. Now you need to keep your equation balanced, right? So if you're adding 1/4 on the left-hand side, you're going to have to add that on the right-hand side as well, right? Otherwise you're messing up the equation. So you get this, and now you're guaranteed that inside the parentheses, you'll be able to factor the y's as a perfect square. Oops, this is a plus here. Be able to factor the y's as a perfect square. Do you know what perfect square it's going to be? Well, it's going to be whatever this quantity is that you squared up here, which was -1/2. So put that in here, right? So there we've got the square completed, and then on the right-hand side, you just have the 1/4. Oh, that's the equation for a circle. That is the equation for a circle centered at the origin. No, it's not centered at the origin. Where is it centered at? What are the coordinates of the center? Remember how to read those off of the, yeah, it's HK, right? Which would be what, 0 and 1/2? Yeah, it's centered at 0 and 1/2. And the radius is what? 1/2, right? It's the square root of the 1/4 here, right? Which is 1/2. Okay. Yeah, Robert, you're obsessed with 1 here, but it's 1/4. Right? Because remember, it's x minus h squared plus y minus k squared equal r squared. So the r is the square root of 1/4, which is 1/2. So we have just a nice circle. Its center is at 0 and 1/2, and its radius is 1/2. Let me see. So I've got this axis kind of marked off in anticipation of having this circle. So notice I've got, I think the 1 is up here on the y-axis. 4 tick marks will give me a 1. So the center is at 0 and 1/2. So right there, and the radius is 1/2, which is so these points that I'm coloring in there, these points are going to be on that circle. So that is going to be your region of integration in the XY plane. If you project that intersection curve there down onto the XY plane, you're going to get this circle. So that's the proper, whoops, that's the proper region of integration. Let me draw my circle. Okay. All right, so how do you guys want to do this in setting up the double integral? When I say how do you want to do this, what I mean is do you want to do it dx dy, or do you want to use dy dx, or do you have any preference on that? Let's fix a value for y first. So let's fix a value for y, for example, right there. And let's set the x vary first. So that means the order of integration is going to be dx dy. X is going to vary first because we're going to fix a y value here. And then, right, we'll integrate with respect to y. So my double integral is going to look something like this. Okay. Now, but remember, we're going to have 2 of these, okay, because I need to compute first the volume beneath the paraboloid, and then I subtract off the volume beneath the plane. Okay. So first, let's find the volume beneath the, let's find the expression, the double integral for the volume beneath the paraboloid. All right. So, well, what's my integrand going to be there? What expression am I integrating? It's this one, right? So 1 minus x squared minus y squared. I'm going to fit that in here, right? 1 minus x squared minus y squared. Okay. And what now will be my limits of integration if we're integrating with respect to x first? In other words, if we have fixed the y value and we're letting x vary from left to right across the region of integration, right? So the question is, what is this? What is that point, right? And what's that point? Is that easy to figure out? What's the equation for that? What's the equation for that circle? Right there, right? Okay, right? So I want to solve here for x, right? Right, so let's solve that equation for, let's just solve that equation for x, right? So we get what? Remember, this is just x squared, right? So I have x squared is, can we simplify this a little bit just for the purposes of solving for x? Remember, all of this was y squared minus y plus 1/4, right? Okay, so let's shift all of that to the, to the other side. So I have a positive y minus y squared when I shift the y squared and the y right to the right hand side. And then the 1/4 are going to cancel, aren't they? So I just get this. Oh, that's nicer, right? And so that means that x is going to be what, plus or minus the square root of this? Okay, so that doesn't look so bad, right? So see, on this side, this is minus the square root of y minus y squared. On this side, this is plus the square root of y minus y squared, right? So there are my inner limits of integration minus square root of y minus y squared, and then positive square root of y minus y squared. What about the outer limits of integration? So this is a little bit easier, right? How is y varying now? Here you'll have constants, so it's a little bit easier to calculate. What? 0 to 1, right? Y is going to go here from 0 down to 1, right? Okay. Remember, you're thinking of remember here, you're thinking of slicing this a bunch of times, right? Computing a bunch of areas and integrating them all together. So each one of those slices has these limits along the x-axis, right? From the left side of this circle to the right side of this circle. But the y is just moving from 0 up to, y is just moving from 0 up to 1. So not so bad at least. Now, integrating that is another matter, right? But at least not so bad, at least setting it up. And so that's the volume beneath the paraboloid down to this region of integration. But it's also easy to set up now the volume for the surface, right? Because you're going to have the same limits of integration. So so once you've sort of found the limits of integration, right, it kind of simplifies things a lot. Except your integrand now will be the equation for the plane, right? Which is what, 1 minus y? So here we just have 1 minus y, and then again dx dy. Now, since those integrals have the same order of integration, right? And they have the same limits of integration, that means I can combine those, right? I can combine those double integrals into just a single double integral with the same limits of integration. So so it's just a matter of adding these integrands together, right? And making sure we combine the like terms properly. So when you add those two integrands together, what do you end up with here? Well, when I say add them, you're actually subtracting, right? So what do we end up with here? Looks like the ones are going to cancel, right? So I like that. You're going to have 1 minus 1, right? 1 here, but minus 1 here. And then this will become a plus y, right? So it looks like we end up with, let's write it in like this, y minus y squared minus x squared. Is that right? Am I doing that right? Dx dy? So finally, there's the double integral that that we have to integrate. It's not too hard to start on this double integral because this is easy to integrate with respect to x, right? You can just use the anti-par rule, correct? But so you can find the antiderivative of y minus y squared minus x squared with respect to x pretty easily. But when you plug in the limits of integration, you're going to introduce some square roots, correct? So it's going to start getting messy. And then you're going to be integrating some square roots, and we know that can be challenging. So actually now we could actually do this by hand. It turns out that we do have the knowledge and the skills to integrate this by hand, but it's a real bear, okay? So it will involve some trig substitutions because of the square roots, okay? So that would take us about 30 minutes, and I don't want to spend that time, okay, on reviewing our calculus 2 integration skills, all right? But there's the expression for the double integral. Let's do this one with Wolfram alpha and see what Wolfram alpha says is the result here. So let me see if I can find Wolfram. There's Wolfram alpha. Okay, and let's see if we can integrate that expression. So that's going to be already just typing that into Wolfram alpha is going to be a challenge for us, but I think we can do that. Okay, so let's see. That's going to be integrate, right? It's just the command, and then you're going to need some parentheses here, right? Because you're integrating an integral. So this is a double integral. Oops, let's make sure we spell that right. Although Wolfram alpha should catch that mistake for us. All right. So what is that? What was that integrand? I forgot. Did y'all write that down? Y minus y squared minus x squared. Was that correct? Y'all didn't write that? It's going too fast. Y minus y squared minus x squared. Unless I made a mistake there. Hope not. Okay. So y minus y squared minus x squared. And now here's the tricky part though. From, let's see, what was it going to be? X equals, and now we have to type in those limits of integration. In Wolfram alpha, if you want square root, you can use the function sqrt. You could also use the exponent 1/2 here, but square root also gives you sqrt also gives you square root. But let's see what. So that was a minus square root, right? So the bottom one was minus square root of, and what was it? The square root of y minus y squared. Okay, 2, and then just the conjugate of that. So y equals the square root of, same thing. All right, so that was the inner double integral. So let's close that now. And then we have to type in our limits of integration for the outer integral. That was from y equals 0 to 1, though, right? So that's a little bit easier. See if we've got our syntax correct. And see what Wolfram alpha tells us here. Thinking about that one a long time, so maybe we didn't get the syntax right. Sometimes you can't tell with Wolfram alpha if it's thinking or if it's or if you've made a mistake. Let's try this again. Well, I did this one this morning, and I think the answer is, we'll see. We'll come back there and see if that actually computed. It computed fast this morning, but we may have typed something wrong. But the answer, I think, turns out to be pretty simple. I think it turns out to be pi over 32. So I think if we were able to get that to calculate, that's what the final result turns out to be. We'll look back there in a second and see if that one has. Generally, if it's going to give us an error, it would have already said that we made a mistake. So I don't know what it's thinking about. It may just be busy. Wolfram alpha takes different amounts of times at different times, depending on how busy their server is. Okay. All right. So just taking the difference, right, of those two volumes is how we compute the volume of that little cap there, right? That little cutoff piece between those two surfaces. All right. Now let's talk about converting these double integrals or these volumes to they don't have to be volumes, but that's the application that we've been using here to polar coordinates. This is going to be useful. Well, you'll see the examples. If your region of integration in the XY plane is more easily described using polar coordinates than it is using rectangular coordinates. And that sometimes happens, okay? Well, we'll see that in these examples. But I would just want to remind you a little bit of polar coordinates so you'll remember these just basic facts about polar coordinates, right? So, of course, all through the semester, right, we've been using rectangular coordinates, at least in 2 dimensions and in 3 dimensions as well. But in 2 dimensions, especially, right, we've been using rectangular coordinates, right, to locate points on a 2-dimensional surface, okay? And of course, you know how rectangular coordinates work, right? You have the 2 coordinates and they give the location of your point, right? Relative to the x-axis or relative to a horizontal axis, usually called the x-axis, right? And then also relative to a vertical axis, which is usually called the y-axis, right? So that's our beloved Cartesian coordinate system. But there are other systems that you can use to also locate points on 2-dimensional surfaces, or also in 3-dimensional space as well. The most familiar of these is known as polar coordinates. So in polar coordinates, you still have to give coordinates for a point, okay? And you still have to use, this is important, okay? You still have to use 2 coordinates, okay? Because you are in 2-dimensional space. So just the physics of the universe requires you to use 2 coordinates in 2-dimensional space, okay, to locate a point. But the coordinates in polar coordinates work a little bit different, right? So in polar coordinates, you're going to locate a point. You're going to give its distance back to the origin, okay, as one of the coordinates. That coordinate is usually labeled the R coordinate in polar coordinates instead of the X coordinate, right? Okay, so that R means it's just sort of short for radius. But if you know the radius of a point, that is its distance away from the origin here, right? That's not enough to completely locate the point, because of course there's a whole circle of points, right, that are this distance away from the origin. So you need a second coordinate to completely locate the point. And that second coordinate is going to be the angle that's formed between the point and the x-axis. Actually, it's the angle formed between the x-axis and this line that connects the point to the back to the origin. Okay, so if you can compute that angle will then completely locate where your point is, right, on your 2-dimensional surface. So you have that usually that second coordinate is referred to as theta instead of y. So remember, in polar coordinates, you have a distance away from the origin, and then you have this angle formed with the x-axis. And those are the 2 pieces of information that we use to locate the point, okay? Now, there are some important equations that you can use to connect rectangular coordinates to polar coordinates. So I want to just remind you of those, okay? If you know the polar coordinates for a point, if you know the polar coordinates for the point, then you can convert back to rectangular coordinates with these formulas, all right? And those formulas are very easy to derive just using a little trigonometry, but I'm not going to derive those formulas for you again here. A little right triangle trigonometry, it's easy to derive these formulas. So again, if you know the polar coordinates of a point, that is the angle and the radius, right, the distance that the point is away from the origin, then to compute the x-coordinate in Cartesian coordinates, to compute the x-coordinate of the point, you just take the radius times the cosine of the angle. And then to compute the y-coordinate, you take the radius times the sine of the angle. So it does take a little trig, but you can convert polar coordinates back to rectangular coordinates. You can also do vice versa as well. So if you know the rectangular coordinates for a point, the x and y coordinates for a point, you can convert those to polar coordinates. How do you compute the r value? Well, the r value, that is the distance away from the origin, is just the square root of the x coordinate squared plus the y coordinate squared. That's just the distance formula. Or you can also think of it as the Pythagorean theorem if you want to. Okay, so so easy to compute the r value. The angle is a little bit harder to compute. Okay, all right, but this is usually the formula that's given for computing the angle theta if you know the rectangular coordinates. But sometimes you have to, since arctangent is not really the inverse of tangent, right? Sometimes you have to think a little bit more carefully about this formula and interpret it properly to get the right angle, okay? But basically, theta is going to be the arctangent of the y coordinate divided by the x coordinate. So these are the conversion formulas for going from rectangular to polar, or vice versa, from polar to rectangular. Let's try those just to remember how to use them. But before we do that, actually, let's try plotting these points. These are points given in rectangular, I'm sorry, in polar coordinates. Let's try plotting them. So let me draw some axes here so that we can try converting these. Okay. All right. So where would that 0.1 and 3 pi over 4, where would that be located? Yeah, it's going to be in the second quadrant. The angle is 3 pi over 4, right? Remember, that is 3 pi over 4, right? It's a multiple of pi over 4. So you're going to have a 45-degree line, but it's the 45-degree line that goes into the second quadrant, right? Okay. So there's the angle 3 pi over 4. And then just along that line, you need to just find distance 1 away from the origin. Okay. That's not always that's not always easy to do by eye, okay? But you get the basic idea there. So I think 1 would be somewhere about right there, right? Into the second quadrant. What about 3 and minus pi over 6? So where's minus pi over 6? Well, that's in the fourth quadrant, right? And that's what, 30 degrees? So we're down here about 30 degrees into the fourth quadrant, and then we're at distance 3 away from the origin. And there, I'm just going to eyeball it here, maybe about right there is maybe distance 3. What about 5 and 3 pi? Where is 3 pi? That's just the same as pi, right? Okay. Yeah, because 2 pi is 1 revolution, right? So 3 pi would just bring you over, to the left side of the x-axis, right? And we want to go out distance 5. 1, 2, 3, 4. Oops, I need to extend my axes a little bit. Right there is 5 and 3 pi. Here's the one that's a little bit hard to interpret. What about minus 4? You can have a negative radius in polar coordinates, but you have to interpret it properly because that's not really going to be a distance, right? So what about minus 4 and pi over 4? Well, if this were positive 4, you would be along this 45-degree line, right? Because that's pi over 4. But with negative 4, you're going to go backwards along this same line, okay? So you're going to go down into the third quadrant, distance 4. Where's distance 4? Maybe right there. So minus 4 and pi over 4 will be in the third quadrant instead of in the first quadrant. Let's try using our conversion formulas. So can we convert this one to rectangular coordinates? So that is that's polar coordinates. So where would that be at? That's 2 pi over 3. Where's 2 pi over 3 here? Over in the second quadrant, right? 2 pi over 3 is about right here. Up distance 4. Well, who knows where that is? Somewhere length 4 along that line, correct? Um, this is where it really helps to have the rectangular coordinates. So let's see what this looks like in rectangular coordinates. So what's the x? Yes, it's r times the cosine of theta. So the r is 4, and so you're going to have the cosine of 2 pi over 3. So this is 4 times, what's the cosine of 2 pi over 3, though? Yeah, it's is it? Yeah, but be careful there. It's -1/2, right? Okay, because we're in the second quadrant. So it's going to be -1/2. So the x is -2, and the y there is 4 times the sine of 2 pi over 3, which is 4 times, well, this sign is positive, but it's the square root of 3 over 2. Is that right? Yes. And so we get what? 2 times the square root of 3, which I think is about, I'm thinking about 3.4. I think the square root of 3 is about 1.7, a little bit more than 1.7. So twice that would be something like 3.4. How close did I get on my polar? -2 and what? 3.4, 1, 2. Wow, I did really good. That was pretty good. I was a little bit too far to the left. It's really a little bit further to the right there, but I didn't do badly. Okay. Um, Now it looks here like I didn't plot this one very well at all. Oh, I see. I got my I did have my axes a little bit not on the grid lines there. So here we have rectangular coordinates. Let's convert those to polar coordinates. So this is a little bit trickier, sort of. So remember, the r is going to be the square root of x squared plus y squared. So that's easy. That's just an arithmetic calculation. So we have the square root of 2 squared plus -2 squared. So that ends up being the square root of 8. Which I think is 2 times the square root of 2. So there's our r value, 2 times the square root of 2. And now the theta, though, is the one that's a little bit tricky sometimes. So we have arctangent of y divided by x. So that's going to be the arctangent of the arctangent of -1, right? Now there's where you have to be, well, maybe not, okay? What is the arctangent of -1? No, that's what now? Um, Actually, your first instinct was correct there. Your first instinct was correct there. It's going to be yeah, see, this is what's tricky about converting back to polar coordinates is you have to remember about the ranges of the inverse trig functions. And the range of the arctangent function is pi over 2 to minus pi over 2. So if you want a negative arctangent of a negative number here, like -1, which is what this is, you're going to get a negative angle. So actually, this is minus pi over 4. Try that on your calculator. Pi over 4 is what? 0.8 or 0.7 something? I think you get something like -0.7 something. Yeah, minus 0.79. Yeah, right. Okay. Yeah. So remember, arctangent gives you angles between minus pi over 2 and pi over 2. So if you want the arctangent of a negative number, it's going to give you an angle in the, it's going to give you a negative angle in the fourth quadrant. That's fine here because that's where we're at, right? We're down here in the fourth. We're down here in the fourth quadrant. So minus pi over 4 works perfectly as our minus pi over 4 works perfectly as our theta value. So so we can write the polar coordinates as 2 times the square root of 2 and then minus pi over 4. But if you don't like using negative angles, you could write 2 times the square root of 2 and what if you go this direction to that angle? What was that? 7 pi over 4? Yeah, you could use 2 times the square root of 2 and 7 pi over 4 would be the same point in polar coordinates. That's one of the bad things about polar coordinates. That's one of the negative aspects of polar coordinates is that points can have multiple representations in polar coordinates. These are not the same coordinates, but they represent the same point, right? That doesn't happen in rectangular coordinates. Representations in rectangular coordinates are unique. You have one set of coordinates for each point, but in polar coordinates, you have multiple sets of coordinates for the same point. Of course, that's just the nature of angles, right? Now, you can also create equations in polar coordinates. Usually, equations in polar coordinates have this form. So you will have the radius equal to some expression involving theta, but not always. Okay, so you don't have to have equations in this form. But here's an example of a polar equation in that form. R equals 5. So that's a constant equation, right? It just says your radius is always 5. So points on this curve are all points that have radius 5. Where are those points going to be located at? So all points that have radius 5. That means you're looking at all points that are distance what? 5 away from the origin, right? Okay, so what are those? Well, there's one of them over here, right? That's 5 away. Up here, there's another one. Over here, there's another one. Down here is another one. But you have a bunch more of them, right? So you get a really nice curve here. That's just a what? That's just a circle. I drew a terrible circle there. That's the worst circle you've ever seen. But imagine that's a circle. Okay. So you see, there's the polar equation for a circle. Now that's nice because circles in rectangular coordinates, their equations are not terrible, but they're more complicated than this, right? So it's very easy in this case to write down this the equation for this circle in polar coordinates. It's just this very simple constant equation. What about theta equal pi over 3? Now usually polar equations do not look like this, okay? Because remember, I mentioned they're of the form R equal. Usually have R equals, usually have the equation solved for R. And then on the right-hand side, you will have some expression involving theta. This one's a little bit different. Here you have theta equal to a constant. So this is also a constant equation in polar coordinates. What is that equation telling you? You want all points, what? Whose angle is what? Pi over 3. What's that going to look like? All points whose angle is pi over 3. It's a line, right? Okay. Just mark off pi over 3. Pi over 3 is about up here, right? So you basically get all points on this line extending also down into the third quadrant, by the way. All of these points, you can write them where their theta value is pi over 3. So that's in rectangular coordinates, you just have a straight line. Well, it's pretty easy to write down equations for straight lines in rectangular coordinates anyway. So polar coordinates doesn't really give us much of an advantage for straight lines. Now, let's look at this one. So this one is kind of a mystery to us, right? R equal 2 cosine theta. So if we try graphing all of the points that match that equation, what are we going to get? One way to try to graph that equation is to do it the old-fashioned way, okay, and pick values for theta. So start picking different angles, fill them into this formula, compute the R value, and then just plot those points and see what sort of curve you get. So that's the clumsy, kind of beginner's way of plotting that equation. We could do that. Let's get a little bit more clever, though. I'm going to try to convert this back to rectangular coordinates. Let me show you how we can do that. So I'm going to take that curve in polar coordinates and convert it back to rectangular coordinates because I'm much more familiar with rectangular coordinates. So that's going to help me maybe have a better idea of what this curve looks like. If you multiply both sides here by r, I'm going to multiply both sides of the equation by r. So I have r squared equal 2r cosine theta. Multiply both sides by r. But now what's r cosine theta? That is better known as x, isn't it? In rectangular coordinates? R cosine theta is x, right? And r squared is x squared plus y squared. Because remember, r is the square root of x squared plus y squared. So r squared is x squared plus y squared. Oh, so there's the equation converted back to rectangular coordinates. You have any idea what that equation is? That's a circle. Yeah, actually, let's show why that's a circle. So it's x squared minus 2x. I'm going to bring this to the 2x to the left-hand side. Plus y squared equals 0. Now let's complete the square on the x squared minus the 2x. I don't have to do that on the y squared because y squared is y minus 0 squared, right? How do we complete the square here? What do you do? We just did it a moment ago. This one's easier. Add 1. Yeah, right. Finally there. That's right, it's 1. You take the minus 2, divide it by 2, that gives you negative 1. Square that, you get positive 1. Don't forget to add it over here as well. Now, how does that factor? That factors as x minus 1 squared. So you have x minus 1 squared plus y minus 0 squared is equal to 1. So that is that's nice. That's a circle. What's the center? Yeah, the circle center is at 1, 0, and the radius is 1. So can we put that in over here? Can I squeeze that in? So the center is at 1, 0, and the radius is 1. So you get this on this set of axes, you get this tiny little circle right there. Okay. Well, look, now there's another case where the polar coordinates are a little bit easier. See, that's not a very complicated equation in polar coordinates, but it's a little bit more complicated in rectangular coordinates. So the polar version of this circle is a little bit simpler equation than the rectangular version of that circle. Now, when, okay, so you guys know something about astronomy, right? So you know that Copernicus, right, he waited until he was dying. He published his book, and of course, what was the controversy about Copernicus's book was Copernicus had speculated, right, that the Earth revolved around the sun, right? Okay, so he had a heliocentric universe. Now that was very controversial at the time because that went against the teachings of the Catholic Church. So that's why Copernicus waited until he was almost dead to publish that. He knew it thought that for a long time before. Actually, other people knew this as well. It wasn't just Copernicus. But unfortunately, but people then started to try to explain the motions of the planets, right? including the Earth, right? In terms of this circular model, they thought that, they thought the orbits were circles. That's what Copernicus thought, which makes sense. But they could not get their observations to work. Okay, they were slightly off. So, and that was for a lot of reasons. Their technology was not so great that they could make really good observations. But of course, the technology improved. So, so then Kepler, using observations from another astronomer, Kepler was able to determine that actually the orbits were ellipses. They were not circles. Okay. And the sun was at one of the focal points of the ellipses, right? Okay. And then that worked beautifully to explain the motions of the planets. But Kepler did not write his elliptical equations right in rectangular coordinates. Kepler used polar coordinates because this greatly simplifies the expressions for the equations. Okay, so just if you're wondering, is it really practically useful to write circles using polar coordinates or write curves using polar coordinates? The answer is yes. Okay, there's a very famous example of that. All right, now what's going to be useful for us is using polar coordinates to describe regions, certain types of regions in XY plane. So think of these as being regions of integration in the XY plane. And let's see if we can write down polar coordinates. We're going to write down inequalities to describe these regions, okay? So notice you've got a region is a whole set of points, right? Okay, so we want to write down inequalities in polar coordinates that will correspond, or the solutions to these inequalities, right, correspond to these regions. And for some regions that might not be easy to do, but because of the shape of these regions, it's fairly easy to write down though. So what can you see about, so think about the polar coordinates for points in this region. What do you know about the R values, the radius value for these points? Any point in this region, what do you know about its radius? It's not equal to 2, right? Okay, because if it's equal to 2, it would be right out here on this curve, right? But all of these points also are part of the region. But their radius is not equal to, but what? Less than or equal to 2, right? Okay, so you know that the R values here are less than or equal to 2. Let's also make them, just to throw it in there, make them greater than or equal to 0. Because remember, you can have negative R values too, all right, in polar coordinates. So we better be careful there and set a lower bound there of 0. Right, so for every point in this region, the radius is between 0 and 2. Okay? But this inequality is not enough, right? Because if you just include this inequality, you would also have points over the second quadrant, right? And points over the third quadrant, points over here in the fourth quadrant, right? Because they also get radius values less than or equal to 2. So we also need to specify the angle as well. So what can you see about the angle there for all of those points? It's between 0 and pi over 2, exactly, right? You're going to have an angle here always, right, from 0 up to possibly as far right as pi over 2. So let's also put a lower bound on theta there of 0 up to pi over 2, right? So that set of inequalities applies, right? That defines all of the points in that, region. What about for this donut region here? This is called an annular region. So here we have the region between two circles, right? Okay. Well, this should be pretty easy also to describe points in that region, because what can we see about their radius or radii? I want to say radiuses, but radii I think is the right plural. Well, remember, you don't get points here, right? Don't get this little donut hole that's cut out of this region, right? So your radius for all these points has to at least be how much? Right. Yeah, because you want to miss those points with radii less than like up to farther. 3, right? Okay. So again, very easy to write that down. We just want R values between 1 and 3, right? I guess because of the way they've drawn this, we'll use less than or equal to. It looks like the circles themselves are included in the region, right? Because they've got solid circles there. So I think we'd use less than or equal to. Now, what about for the theta values? That's right. You go all the way around the circle, right? Okay. All the way around the circle. So you can have angles actually from 0 all the way to 2 pi. This is a little bit redundant because you have an angle of 0 and an angle of 2 pi, you're going to get points along the x-axis, right? Okay, so some points actually, you might be doubling there, right? By including both boundary values there. You could actually now, if you like, make this much higher, but it's not necessary, right? Okay. So if you wanted to go to 6 pi or 8 pi or some other larger multiple of 2 pi, you certainly could, but it's not really necessary for capturing all of the points, right, in that so-called annular region. Now, the third region is that's obviously tougher. Okay, it's hard. This is called a cardioid, because it's shaped like a heart, but the heart's kind of turned upside down. So, kind of shaped like this, right? Kind of like a heart. So that's why this black curve is called. The equation for that curve is r equals 3 plus 3 sine theta. So if you plot in polar coordinates 3 plus 3 sine theta, get that cardinal curve. So that's not a type of curve that you see in rectangular coordinates at all, right? Might be fun to try to convert that to rectangular coordinates and see what the rectangular equation for that curve is, but I'm going to tell you it's going to come out to be complicated. So it's not going to be pretty. So that curve is much easier to describe in polar coordinates than it is in rectangular. All right, so, but how do we describe that region of points inside of the cardioid? Okay, well, the trick to realizing what to do here is values that are on the points that are on the cardioid, exactly on the black curve, their R value is exactly 3 plus 3 sine theta. Okay, all of these points, their R value is exactly 3 plus 3 sine theta. So if we want points inside of the cardioid, we just need to change this equation to what? Just change it to an inequality. So just take R values less than or equal to 3 plus 3 sine theta. That will give you points both on the black curve, where the R values are exactly equal to 3 plus 3 sine theta, and then also points inside of the curve. And again, you can restrict your R to be greater than or equal to 0. For the theta, that's a little bit harder to understand. But since that cardioid is a closed curve, right? It's a closed curve. That is usually a signal that you're going to let your theta run in from 0 to 2, okay? Like a circle. So, I'll just tell you here the correct values for theta are 0 and 2 pi. Normally, if you have in polar coordinates a closed curve like this, theta will run from 0 to 2 pi. Now, the reason we're interested in writing down these descriptions for these regions in polar coordinates is I want to use these regions as regions of integration for a double integral. And here's the theorem that is going to allow us to do that. Okay. All right. So this theorem has some lots of conditions on it. So I don't need to explain all of the conditions. Okay. Let me just tell you how we're going to use the theorem. Although sometimes the conditions become important, but usually the conditions will be satisfied. Okay. All right. So, but this theorem says, suppose that you have a double integral that you want to, right? So you're computing, sort of think of this as volume beneath some surface, right? So this is a surface in rectangular, it's above some region in the xy plane. So they didn't put the specific limits of integration on it. But you would choose the limits of integration to match whatever this region is, the xy plane, right? That you're computing volume of. To this surface. Now, what you can do is, if you're able to write that surface, if you're able to write that region of integration in polar coordinates, then you can convert double integral. This double where the variables of integration are polar coordinate variables, not rectangular. So what are these limits of integration? These are just the description that you're using for polar coordinate description that you're using for the region of integration. Notice now that in your function, your two variable function, right? You're just plugging in the polar coordinate versions of x and y, right? X is r cosine theta, and y is r sine. So you're just sort of taking this function and converting that function to polar coordinates, just plugging in polar coordinate equivalent for x and the polar y. There's one catch here, but there's a slight difference. I have to throw in extra factor. Notice that is not in, that's not in original double integral, okay? But when you convert that to polar coordinates, that's an extra factor. Notice the limits of integration also, notice the order of integration also is almost always going to be dr. So we'll integrate with respect to r first and theta second. That means that these limits are limits on r, and these limits are limits on theta. Though you find those limits from considering region of integration of polar. Okay, let's try setting up one. The integration now here part is not all that crucial to us. Okay, it's setting up the polar coordinates that I want to make sure we get. Let me see if I can try one here. Oh, by the way, now there are some restrictions on the region of integration in polar coordinates, but I'm not going to. I don't want to get bogged down in details on these restrictions. These restrictions are almost always going to be satisfied if we're able to describe the region of integration in polar coordinates. These restrictions are almost certainly satisfied. So let's find an example and see if we can set this up. All right. So here's what we want to do. We want to find the volume beneath this surface x squared plus y squared, but above this region. Okay, no, I'm sorry, it's just x squared plus y, not x squared plus y. Um, so beneath this surface, x squared plus y, but above this region. So this donut region again is called an annular region. Okay. So you see, that's difficult to describe that region in rectangular coordinates. That's a hard region to describe, but it's just very easy describing. So that's why it's convenient to try to convert this volume problem, which is going to be a double integral problem, right? That's why it's easy to or it's easier to convert this to. Okay, so let's see if we can we describe this region using polar variables. So let's see what that region. This inner circle is that's a circle. Its equation is x squared plus y squared. And this outer circle, its equation is x squared plus y squared 5, right? So this thing is not drawn to very good scale. That means that this point is going to be 1 on the x-axis. And what is this point going to be on the x-axis? What's the radius of this outer circle? See, there's its equation. So what's the radius of that outer circle? Yeah, the radius is square root of 5, right? So that means this number on the x-axis is square root of 5, not 5. So I didn't draw a very good picture of that. Well, maybe I did. What's square root of 5? 2.2? Oh, so maybe this isn't so bad after all. A picture of this region. All right, so let's see if we can write down a description of the region using polar variables. So what is the restriction on our R? So what's the smallest value of R you can have for points in this region? 1? Yeah. Going up to, what's the largest value? Square root of 5, right. And now what about restrictions on theta? Yeah, this is a complete, annulus is a complete circle, right? So that means that theta is going to run from 0 to 2 pi. If you cut theta off at, say, pi, then you would have just the top half of the annulus, right? Okay, 0 to pi would just give you the top half of the annulus. Oh, all right. So there's the description of our region of integration. So let's try writing down the double integral for this volume, right? So, but in polar coordinates. So what are we going to have here? I think we can figure out now what the limits of integration are, right? Remember, the order of integration is dr d theta, right? So the inner limits of integration correspond to r. So what are our limits of r here in this region? Isn't it 1 to square root of 5? See, easy, right? And what about for theta? Zero to 2 pi. Easy. See, that would have been a nasty limits of integration trying to do this in rectangular coordinates because we have a bunch of squares and square roots and right? So we have that nasty integration, polar coordinates, simple. It's constants. Now, how do we find the integrand? Remember, you take the polar version of x and the polar version of y and plug them into your function formula. What was our two variable function here? Wasn't it x squared plus y, right? So in other words, evaluate f of r cosine theta, which is the same as x, r sine theta, which is the same as y. So let's see, what would we get there? R cosine theta squared, right? That's x squared plus then just r sine theta. That's it. So that's really r squared cosine squared theta plus r sine theta. But here's the tricky part that's easy to forget. What do I also have to multiply in here? R. Ah, so there's what we're actually going to, there's what we're actually going. Let's save that evaluation for a second here, and we'll come back to that because the rest of this will just be, this is just going to be some calculus. It's really not even that bad calculus. Okay. Let's save the evaluation for, let's come down and set up another example, and then we'll come back and see how far we can get with the evaluations. I've just got one more example I want to set up. Okay. All right. There now you actually get a picture. All right. Okay. So we're trying to find the volume beneath this surface, which is this hemisphere, that is square root of 16 minus x squared minus y squared. Okay. But we only want the volume of that below that hemisphere above this region. Like, so we don't want the total of the sphere's volume, but just the piece above this region, which happens to be, fortunately for us, a circle. Okay. So in other words, I want this kind of cylinder, right? But it's not quite a cylinder, it's the top of it. It's sphere. Okay. So that little plug. So that's the volume beneath a function, right? This function square root of 16 minus x squared minus y squared down to a region in the xy plane. But let's see now if we can describe that region efficiently, saying polar, because maybe that would be easy. So this description of that region in so this region right here, see if I can outline it. Yeah, that region right there. What's that going to look like in? So there it is. There's a description of the region in rectangular coordinates. What's that going to look like in? What's that going to look like in polar coordinates? So let's write that down in polar coordinates. So what's the limits on the R for this region? 2. Yeah, okay. Because that region is really just a disk, right? That's just inside of a circle, and its radius is 2. Okay. The edge here that I drew, the edge of the circle, right? Its equation is x squared plus y squared equals 4. So you can see that's a circle, right, with radius 2. So you want radius values between 2 and 0. And what about for your theta values? There you go, from 0 to, again, from 0 to 2 pi. So it should be really easy then to write down our, maybe, right? To write down our polar double integral, right? For this volume. So let's see, the limits of integration, very easy. What is it for R? Just 0 to 2, right? And for theta, just 0 to 2 pi. So we get really simple limits of integration. What about for the integrand? Well, that's a little bit worse, right? Because we have to plug the polar coordinates, right, for x and y into this formula. So when you do that, let's see, what do we get? We would get 16 minus, what's x in polar coordinates, though? That r cosine theta? So we would have r cosine theta squared, right? And then minus y is r sine theta, right? Squared. And there's our function. But again, if we're going to use polar coordinates, we have to remember to add one additional factor, right? What do we also have to multiply into the integrand? R, yeah. So must also there multiply in R. In this case, I think that turns out to be very useful, though, okay, in actually evaluating this integral. All right, let's try. So we have a few minutes left, so I'm not sure we're going to get both of them, but let's try starting this one and see how far we make it. Let's see how much of our integration knowledge from calculus 2 or wherever we need to actually recall. Boy, I hope I have enough room here. Not sure that I do. There's never enough room for computing integrals, so that's just a rule of thumb there. Okay, so let's start there let's try simplifying things under the square root a little bit. Okay, because that's really nasty, right? The way it's that's really nasty, right? The way it's written. So let's see, what can we do there? We can, of course, we can square the r cosine theta, right? And the r sine theta. So we get 16 minus r squared cosine squared theta minus r squared sine squared theta. Yeah, Robert. So because why would we want to do that? Yeah, because of the Pythagorean identity, right? So so that's kind of staring us in the face here. So let's see if we can apply that. So factor out the minus r squared from both of these terms. And that would leave you then with cosine squared theta plus sine squared theta. And so we're just in great shape, right? Because that is 1, right? So you can just wipe that right out. And so now you have a much nicer antiderivative. So you have the square root of the 16 minus r squared, right? I think now a substitution will work. Okay. Whenever you see square roots, by the way, that's side of integrands. That is scary because usually the way you deal with square roots in integrand is using trig substitution. But I think this one we get a little break on because of this factor. Okay. R is close to the derivative of 16 minus r squared, right? Derivative of 16 minus r squared is minus 2r, right? And this is r. So that means that just a simple substitution affected integrating this square root. So let's try that. So see what I'm suggesting is try u equals 16 minus r squared. Okay. So then let's see, what's du dr? Is that minus 2r? Which means dr is what there? du over minus 2r, is that right? Du over minus 2r. So let's make this substitution. I'm not going to bother to change my limits of integration because I'm going to undo this substitution in a moment. Okay, so we are going to switch back to r eventually here. Okay, but so it's not worth the trouble to try to fix the limits of integration. So I get r times what? The square root of this is u, right? And then dr is du over minus 2r. But don't forget now, I still got the d theta hanging along there, right? So nice things happen, right? Because let's see, that's what I was predicting. R's cancel, and this minus 2 you can factor out, right? So you can factor out the minus 2. So we see we get a much more palatable here integral, right? So I factored out minus 1/2 right here. I should probably put in some grouping symbols, but I'm going to, okay, factor out minus 1/2. And then what's left under that first integrate is just what? A square root of u du. And then here's the d theta. And so what's the antiderivative for that? Yeah, right. Okay, so
That would be the derivative.
I'm sorry, what's the antiderivative? Yeah. Okay. You're going to use the anti-power rule. Remember, square root of u is the same as u to the 1/2 power, right? Okay. So what do we get there when we find the antiderivative? Is what u to the 3/2 power, right? Divided by 3/2 exactly. Okay. And then we're going to evaluate that from what? 0 to 2? But now, before we do the evaluation, you have to undo your substitution, okay? Because these limits apply to R, right? Not you. So let's go back and right value. Just go back and fill in what the right value there is, right? For u, which was what? 16 minus r squared? So we have 16 minus r squared to the 3/2 power. Don't forget that's divided by 3/2. And then we're evaluating that from 0 to 2. Let's see, we need to deal with the 3/2, right? So just inverse take 1/2 and find it by 2. Okay? So that's 1/2 of minus 1/2 of minus 1/3. So really this fraction is minus 1/3, and I can erase this. And now just fill in our limits of integration. So it looks like what? Minus 1/3 times, let's see, when you plug in the 2 there, is that 12 to the 3/2? 16 minus 4. And then when you plug 0 in, you get just 16 to the 3/2, right? But don't forget, all of this is multiplied by -1. Now, look, we still have some work to do, right? But this is much easier because when we have inside of factor inside of and for our integrate, then we have some arithmetic. All of this is just what? That's right. All of this is just a constant, right? You're integrating respect to theta. So ultimately, you take the ultimately here when you take this derivative, you're just going to get what? This constant multiplied by theta. Okay, so get a very simple antiderivative here, okay, from 0 to 2 pi. Let's see what these. Do we have time here? See what these numbers are. So let's see if we can figure this out. What is 12 to the 3/2 power? Shall we write that down somewhere else? 12 to the 3/2 power. So that means the square root of 12, right? Cubed. What's the square root of 12? Right. So this just come out to be 12 times the square root of 12, right? When you cube that. But square root of 12 can be simplified also because that's 12 is 4 times 3. So I think you ultimately get here 24 times the square root of 3. Right? 12 is 4 times 3. Square root of 4 is 2. So you can extract a 2 to multiply by the 12 to give 24, but you'll still have the square root of 3 left, right? Okay, so all of this is 24 square root of 3. This must be very easy. What's 16 to the 3/2 power? Is that 48? No, I did that wrong, right? 64? Yeah, the square root of 4 cubed is 64, right? Okay, so I still have integral from 0 to 2 pi minus 1/3 here of, let's see, we said that was what? 24 times the square root of 3 minus this is what? 64? And now we have minus 1/3 of that. So what does that give us? Let's see, minus 1/3. So what? 64 thirds minus 8 times the square root of 3. Am I going too fast there? This is minus 8 times the square root of 3. This is positive 64 over 3. But when you integrate that, I mean, when you find the antiderivative of that, right, you just plug a theta there, right? So you get all of this, 64 thirds minus 8 times the square root of 3, all of that times theta, and then evaluated from 0 to 2 pi. But of course, when you evaluate that at 0, that's nice. You just get what? 0? So it looks like here we have 64 thirds minus 8 times the square root of 3 times 2 pi as the, there it is. Oh, I wonder if we made an arithmetic mistake somewhere in there. What do y'all think the chances of that are? Probably pretty high. That looks like close to the right answer there. All right, so I'm going to go back and check that. We'll go back and check that for the arithmetic. Okay. since we went so quickly there. All right, but there finally is an expression. We might be able to simplify that some, but there's an expression, right, that we can use for the volume of, what was that the volume of? I forgot. This cylinder, right? Beneath this sphere. Oh yeah, the volume of this piece. Okay. All right, well, it looks like now we've got just this. We just have to try to see if we can get through that evaluation, see how bad that is. Okay. That one might be a little bit messier, but I still don't think it's all that bad. Okay. To evaluate that integral. Okay. But let's say that that's going to take us a few minutes, so we won't have time for that. Now, here's another really beautiful application of here's another really beautiful application. So we're not going to do this one, all of this one either, but we're going to understand the idea. So here we're not computing a volume. All I want to find is the area enclosed by this kind of a over. So I want to find the area in two-dimensional enclosed by over. Wow. Now that's now there's a college level problem, right? So I want to find this area. So I want to find a two-dimensional area there. So it's not a volume. Now, do you recall how we found, but we found two-dimensional areas using double integrals already, right? How did we do that in the back with rectangular in the plane? Remember what we used as the integrand? One, right. So that's exactly what we're going to do here. We're going to set up a double integral, but using just the integrand of 1. All I have to be able to do is figure out, how to describe this region with polar. So if I can figure out how to describe that region, polar coordinates, then oh, I've almost got it here. Okay. Oh, it's a little bit more complicated than just the one, because remember, you also, what do you need included in your integrand for your polar coordinates? You always need that factor of r. All right, so it's going to be 1 times r. But I've got to figure out what are the proper limits of integration. I do know, by the way, the formula though for the 3-leaf. Well, here it says called a rose. Okay, for this 3-leaf clover. There is the polar equation for that curve. Wow. Wonder what that curve would look like in rectangular coordinates. I bet it's going to come out really crazy. But in polar coordinates, it's a very simple equation, just 3 times a cosine of 3 theta. I think if you change this number, that's the coefficient on the theta, you can get more leaves on your rows. I think this 3 is just the radius of the rows. Notice that along the x-axis, this stretches from 0 to 3. So I think this coefficient controls the radius of that rows. This coefficient somehow controls the number of leaves on the rows. But you get a very beautiful curve, right, with a very simple polar equation. So we'll see next time if we can set up the limits on r and theta that will describe this region. Okay. All right. And then you're calculating a very complicated area. That's a complicated area, but we're able to calculate that now, right? Using a double integral. Okay. let's stop there. Well, so we went right through the break today. Sorry about that. But I had to get polar coordinates out of the way. So we're on good shape. Okay. Next time we're going to look at maybe some of the polar coordinate homework that's due at the time of the test, and then talk about a little bit more about triple integrals. But they sound intimidating, but they're actually turn out to be easy to set up. Okay, not easy to evaluate always, but at least easy to set up. Triple integrals for computing volumes. Okay, so we'll stop there. I'll see you guys on Wednesday if we're not dead from the water. See you on Wednesday.